All right, we're in 6.2 now, Advanced Calc students, and this is the mean value theorem, which I hope you've seen before. But really, the trick to the problems in this section are using it cleverly and trying to think about interesting intervals and functions to use to make this work. So question 5 has like A through H. We're going to do just the first two. So it'd be good practice to try some other ones here. And it says, use the mean value theorem to establish the following inequalities. You may assume any relevant derivative formulas from calculus. So the first one is we're trying to establish that e to the x is greater than 1 plus x for x greater than 0. And so a common trick is to, for the mean value theorem, is to pick probably the weirdest function here. This can kind of be related to intervals, but this isn't really an interval. So I should probably pick e to the x. And then the interval I'm going to think about, well, I want positive numbers, so let's do 0, and then I don't know where to stop, so let's just stop at an x. And that says that there exists c in there, element of 0x, such that f prime of c, well, and of course, f prime of c is e to the x is the same derivative, so e to the c is going to equal e to the x minus e to the 0 over x minus 0. So let's simplify that. And I'm running out of space, so let me go ahead and block this off, and then I'll delete some stuff. So e to the c equals e to the x minus 1 over x. All right, so let's try to get our inequality based off of that. Okay, so I've got a bit more space down here. Let's simplify that. Let's multiply across. So you have e to the x minus 1, and then x times e to the c. Remember that c belongs to 0 to x. So e to the 0 is 1. So all of that is at least 1. So that's greater than, now we're going to bring in inequalities. That's greater than just x. And if I add 1 to the other side, that's the inequality I was looking for. X plus 1, or they had 1 plus x, but that's the same thing. So I had to get pretty creative with the regions I used for the mean value theorem, but the more you see that and the more you do it, the more comfortable you get. So you'll see a similar trick on the next one. All right, so let's clear this stuff. And then the next one is about logarithm. So let's go ahead and do that. And the inequality we're trying to show for 5b is we're trying to show that x minus 1 over x is less than ln x is less than x minus 1. This is for x greater than 1. So probably the function I would guess is ln x, and then my interval, I'm going to probably do 1 to x because I want x bigger than 1. So let's try that. The intermediate value theorem says then you have a c. So already this way, there's a c in there, so that f prime of c, which is, remember the derivative is 1 over x, so you plug in c, you get 1 over c. And then you take ln x, what was that? Ln x minus ln of 1 over x minus 1. You take basically the average slope. Okay, well, ln of 1 is 0. So let's take this stuff and simplify. Let's go down here. And I have ln of x is equal to 1 over c times the quantity x minus 1. And I want to show that ln of x is less than x minus 1. Well, think about this thing. This thing is, c belongs in there, so c is bigger than 1, so that's a number less than 1. So that gives you the right side inequality. But another way to spin this is that 1 over c, because c is less than x, is that 1 over c is, let's see, so how's that compared to 1 over x? X is a bigger number, so 1 over c is a bigger thing because it has a smaller butt. So I can also say that this expression here is greater than if I replace c with x. And this is the other inequality you're looking for to start. All right, so basically on both those, you use the mean value theorem to start, and then you use inequality facts that we've been working on all semester. Okay, let's go ahead and go to number 6. And on number 6, you want to prove a fact or some proves the necessity of things about Rolle's theorem. Rolle's theorem said if you had a closed interval that you're continuous on and you're differentiable on the open interval. So what are the things you need to be continuous on closed interval? You need differentiable on the open interval. And then you needed, third factor is that you needed the endpoints to be the same. And I want to take away one of those and find something that fails the result. The result was supposed to be there's a C in the middle in AB open where the derivative is 0. So let's take away the bottom one. So if I cross this out first, and you have the first two, so I want a continuous and differentiable, an easy function that I don't have the same beginning and end points, but I also don't have a zero derivative in the middle. So something like this, that would just be y equals x, that on 0, 1 closed. That fits our description, and it is 0, but at 0. It's never 0 in the middle of the interval. So that works for crossing out the third option. Okay, so if I want to cross out a different one, let's cross out differentiable here. So it's continuous, not necessarily differentiable, has the same outputs. Well, continuous and not differentiable, your go-to function should always be absolute value x. Now I want the endpoints to match. I just can't draw. So let's do absolute value x on -1 to 1. That is not differentiable at 0. That should be at the origin, sorry. And the derivative is not 0 there because f prime of 0 here feels like it should be 0, but it does not exist. So Rolle's theorem, it does not apply, and it's because you're not differentiable on the whole closed interval. All right, so that's if you cross that one out. Now we want to say that it's not continuous on the closed interval, but it is differentiable on the open interval. So that means I have to have some sort of issue at an endpoint, and I could do like an asymptote, but an asymptote wouldn't have equal endpoints. That doesn't make sense. So let's do a jump discontinuity instead. So let's go back to this one and tweak it and just make the y value up here. That's differentiable, so that's y equals x, except I changed the at 0, I made f of 0 or y of 0, 1. So that doesn't work because the endpoints match, but it's not continuous on the whole thing, and you still don't have a derivative ever equaling 0 at all in this case. All right. So those are the 3 ways to screw up Rolle's theorem for number 6. Okay, 8 wants you to prove a fact from calc that we just kind of took to be clear, which is that a positive derivative means increasing and a negative derivative means decreasing. So we're just going to do part A, and we want to say if the definition of increasing is given, but you know what that is. So f prime is f is increasing if only if f prime is greater than or equal to 0 for all x in the interval. Okay, so we're going to do this 2 different ways. It's if and only if. And so let's start with the positive derivative. That's where we're going to use the mean value theorem. So you have this thing on some interval, so we'll say AB. Let's just make a comma there. That looks terrible. A, comma, B. Okay. And so I want to show that if you have x1 less than x2, I'm trying to show increasing, I need to have f of x1. Now I don't need strictly increasing here. I need less than or equal to f of x2. Okay, well, the mean value theorem says that f of x2 minus f of x1, think of those, not AB, think of these as the points for the mean value theorem, and then x2 minus x1 is equal to f prime of some c in between them. But f prime of c is positive, right? So you have f2, f of x2 minus f of x1 is equal to some positive derivative and then x2 minus x1. Okay, so this is all, sorry, that should be x2, not x squared. But that's all positive stuff. And so that means their difference is positive, which means that f of x2 is greater than or equal to f of x1, right? Because their difference is not only non-negative, but strictly positive. All right, so that's one way. If you have a positive derivative, it's increasing. Okay, let's go the other way. So now I want to say, some more stuff here. Now I want to say that if you are increasing, you have a positive derivative. Of course, we're taking it to be differentiable also. Okay, so if we want to take f to be increasing, then if we have let's say that x is greater than c to start. So what would this look like? So thinking of c as a particular point, and then thinking about what this would look like. So if x is greater than c, then f of x minus f of c should also be positive because you're increasing. This should also be positive. So that should look like that. And then if you take the limit of that, that'll stay positive, and that's exactly what a derivative is, right? If you take the limit here as x goes to c. So if you have a bunch of positive terms, you take the limit, it'll stay positive or non-negative. Now, if x is less than c, let's think about that for a minute. It's a different color. If it's less than c here, well, these would both flip, right? Because by increasing, so this would stay the way you want it to stay. Okay, and then the proof works exactly the same for part B. It's showing if it's negative, non-positive derivative, then it's decreasing function. Okay, so that was 8. Now I want to go to 17, which was a similar idea, if I remember right. So you have two functions differentiable, f and g, and f of 0, g of 0 are both 0. Or no, sorry, they're equal. They're not necessarily 0, but they're, let's stay in red. Now f and g are both differentiable, and I already know that one derivative is less than the other for all x greater than 0. They start at the same spot, and one derivative is above the other, and show that the functions follow the same route for all x greater than 0. If they maintain the same order. So if g prime is above f prime, g is above f. Okay, so common trick in this whole chapter, and even in continuity, is to think about a different function. So we're going to think about g minus f. Suddenly my stylus is crapping out. Let me give you that, guys. Okay, so g minus f. And we're going to apply the mean value theorem to that. And notice that h of 0 equals 0 because that's the reason why I created h, because I now have a point that I know. And I also know that h prime of 0, being the difference of these, is positive the whole time. So now if you take some point c in 0x, like we've been doing quite often, then you get h prime of c, which is positive. That's going to be h of x minus h of 0, which is 0, over x minus 0. And so you get, this is a positive term, times x is positive. So altogether you get h of x being positive. And remember, h is f minus g, so that takes you right back to this. All right, and that is everything for the ice sheet on 6.2.